Percentages were introduced in section 1.3 when we discussed isotopes and their percent abundances. Even so, we'll start this video with a brief review of how percentages work. All of our percentages can be boiled down to a part over a whole. To convert that fraction to a percent, we multiply by 100%. Now, in order to end up with this percent as our unit, the unit in the numerator of our fraction has to be identical to the unit in the denominator of our fraction. Or, in other words, the units have to cancel across that division bar, so we'll just be left with the percent. If we're working with a percent by volume, we could expect the units to be something like milliliters or liters in both the numerator and the denominator. Either milliliter or liter would represent a volume unit and therefore a percent by volume. You could have milliliters in both places or liters in both places, but you can't mix and match. Even though milliliters and liters are both volume units, they are not the same volume unit, and that's what we need for the units to cancel. If we're working with percent by mass, we would expect the units to be in grams or some variation of the gram. Again, the units in both the numerator and the denominator must match. Notice that it didn't matter what the initial units were. In both of these cases, we ended up with 10% because the part and the whole were the same numerical value. Some percentages are pretty easy to work with. For instance, maybe I want to know the percentage of this fruit bowl that the apple represents. There are 6 total pieces of fruit in the bowl, so 6 is going to be that whole. There's a single apple in the bowl, so I would place a 1 in the numerator to represent the part. The fraction would need to be multiplied by 100% to move to the percentage, which I calculate as 16.7%. Because there's a mixture of fruit in the bowl, we could calculate the percentage of different parts of it as well. For instance, there are 2 limes, so that calculation would be 2 over 6, or 33.33%. Or maybe we need to know what percent of the bowl is citrus. The sum of the 2 limes, the lemon and the orange, would give 4 parts total, or 66.7%. Now, all 3 of the calculations we performed with the bowl of fruit here use the same denominator because all 3 cases were concerned with the same whole, which is the total number of pieces of fruit. When we move to chemical formulas, we're going to use molar mass as the same whole for every individual type of atom that we calculate the percent composition of. It's not terribly likely that I ask you to determine the percent of an atom count in a formula, which would be equivalent to what we just calculated. Instead, it's more likely that you have to determine the percent by mass of a certain atom in a formula. This can also be mimicked with our fruit bowl, so we'll do it. Now let's start with the percent by mass that our apple represents. As a reminder, the percent by count for the apple was represented as that 1 apple over 6 total pieces of fruit. Now instead of count, we have to worry about mass. So let's assume that all of our pieces of fruit have a mass somewhere in the standard average range for that particular piece of fruit. Instead of a count in my denominator, I'm going to have a sum of the masses of these 6 pieces of fruit in my denominator. If you could see them better, you too could add all of these individual mass values up and come up with 618 grams. Now the single apple has a mass of 165 grams. We're going to multiply this fraction that we would get by 100%, and we would determine the percentage. Determining the mass percent of an element in a chemical formula isn't very different from what we just did with the masses of those fruits. Let's say we want to know the percent of sucrose here that's attributed to carbon. To perpetuate this bowl analogy, the chemical formula could be broken down to fill our bowl, and it would look something like this. Now this is the point where you need to remember that the subscripts in your chemical formula are really just going to be mole ratios. So that 12 behind the carbon could be repurposed as 12 moles of carbon for every mole of sucrose. And since we're now thinking in terms of a single mole, I can pull that molar mass off the periodic table. So each of these 12 moles of carbon is going to have a mass of 12.01 grams. Similarly, each of the 22 moles of hydrogen is going to have a mass of 1.01 grams, and each of those 11 moles of oxygen are going to have a mass of 16 grams. Now, the denominator for the mass percent is going to be the sum of the masses of all 45 of these atoms. And yes, that value is equal to the molar mass of sucrose, which you know how to calculate. So yay. Now on to the numerator. It's going to be equal to the entire contribution of carbon to that overall molar mass we just put in the denominator. Note that I didn't say the contribution of a carbon, I said the total contribution. We had to add the masses of 12 moles of carbon when determining the molar mass, so the mass of 12 moles of carbon is going to have to be placed in the numerator. Despite throwing a chemical formula into the mix to complicate things for this part, we haven't actually complicated things in terms of actually calculating. So you'll still need to convert this fraction to a percent and then calculate the final answer. You might be saying to yourself, surely she doesn't write the atoms in a bowl every time she's calculating the percent composition. And you are correct. No, I definitely do not. That was just for illustrative purposes. If I needed to be able to calculate the mass percent of any atom in a compound, caffeine for instance, I might do something like create a table that lists all of the atoms, how many of that atom are present in the formula, and what the mass of 1 mole of that atom would be as found on the periodic table, and then what the contribution to the overall mass would be for that many moles of that atom. Pro tip, this is a great way to practice calculating molar masses of compounds if you aren't comfortable calculating them yet. Now, this setup allows me to pull the part and the whole and calculate carbon's mass percent quickly, or hydrogen's mass percent, or nitrogen's mass percent, or oxygen's mass percent. And I can even perform a quick double check on my calculations, as all of these percentages should come really close to 100%. Now in this particular case, these values sum to 100.1%, but that's due to some variations in rounding.